Welcome back, everyone! Alright, we're back with another hype Blue Lock match. The Japan team, our main characters, are back after a 4-0 win against Nigeria, but now they're up against their toughest opponents yet, the France team. Will Blue Lock be able to use calculus skills in order to pull away with a victory, or is France too good for them? Let's begin with things. Alright, we can see the crowd going wild, but how big is the crowd? So as you can see here, the audience is growing at a rate of t to the x equals 80 to the power 80x to the power of 3, 160x to the power of 2, plus 160 per hour. And every x equals 1,000 people. I did this because my first numbers were a little too big for that. What is the rate of change after 30 minutes, 1 hour, 1 hour 30, and what would the IROC be at at what time would the IROC be at 600 per 1,000 people per hour? Let's find all of these right now. So first, we have to take the derivative of our original function. How do we take the derivative, you might ask? That's a great question. Do you see this number up top? We're not going to use the h method. That takes way too long. Instead, we're going to multiply that top number by... can you see my mouse? You can see my mouse. Awesome. We're going to multiply this top number by this number right here. So, let's ask your audience, what is 3 times 80? Was that 240? You're absolutely right. All right. So now, after you've done that, we subtract 1 from the 3 slot. So that would be 240 x to the power of 2. Now we do that for every other function. So times 2, 320, minus 1, x. 180 x. Oh, where's this number? We can just imagine x as x to the power of 1. So what's 1 times 180? Oh, wait. That's 180. All right. And where does the x go? X to the power of 0. What would that be? 0. Or 1, I guess. It's technically 1. Okay. Now that we have our derived form, we need to find out when this is true. This equation that we have right now, this one right here, is true everywhere. But we're looking to find when it's true for specific points. So now, we're going to plug 0.5 in, which is half of an hour. And since we're measuring in hours, that should give us our total. So, plugged in our numbers, and then we get 1,000 people per hour. I know these units are annoying, but it's the best I could do with these numbers that I had. All right, now let's go over here to the 1.5 hour. Where is my 1 hour thing? That's a good question. The 1 hour's not important. All right, it's gonna follow the same rules anyways. So we plug 1.5 hours in, and get our answer. It's going at that rate. Now, what will be 600? That's a great question. So we're able to plug our 600 in for where our t to the derivative of x, or t to the x usually is. So let's rearrange. We move the 600 over to the 420, and then I believe I divided by 20 here, which saved me a lot of trouble. I can divide by 20 because the other side is 0, and it won't really change anything. Let me turn this music down a little. So now we're going to use the quadratic formula, which is right here, to plug in and find out when it's true. And we see here, it is true at 0.814 hours. Don't ask me how many minutes that is. I'm sure I could do it right now, but that goes against the purpose of this. Okay, now let's see which crowd is growing at a faster rate, Japan's or France's. So we see France's crowd is growing at a rate of this right here, and Japan's is growing at a rate of this right here. Who will have the higher IROC after an hour 30 minutes? Well, I'm sure you can't tell just by looking at this. But if we use the principles we learned in the last question, we should be able to solve this. So you can see us deriving the question here, here, and here, going from here to here. And when we plug in the 1.5, we can see that France, which is this side, will be growing at a faster rate of people at an hour or 50 minutes, or hour 30 minutes, than Japan will. So we can see that the France side is growing to be more, or it's growing at a more popular rate than Japan's. Let's move on to the next question. All right, the game starts, and Loki and Charles and the rest of the France team run up the field. As you can see, Loki's here and Charles is here. Loki is the big threat. He's one of the members of the new Gen 11, which are the 11 best under 20 players in the entire world. That's pretty impressive, right? So, Loki's making a big run, and our other new Gen 11 member, Hugo, I'm telling you, France is a really good team, two Gen 11s. sends it past all the way up to Loki, as we can see right there with this breathtaking animation. All the Japanese defenders go onto Loki, but Charles manages to trap the ball and then takes a wild shot at the net. Goal! France starts the game with a goal right off the opening kick. That's insane. You see Hugo talking about Destiny, Charles and Loki celebrating, but we have a very important question to answer. How did Charles get this goal? Well, he obviously used calculus to get this goal. If the equation of Charles' shot is x equals, look at all that. What is the tangent of Charles' shot? 1 meter after its mid-x direction. It's a great question, and it must have been really important to Charles when scoring this goal. I did one of the number graphs for Desmos, as you can see here, and it gave me this really ugly equation. But I was like, I really want to hit these points, right? Because I feel like it makes the most logical sense to hit these points. Should not have done that. It was a pain to solve. Okay, let's see. So we have our x here, and now we're going to do the same thing we did for the last question. We're going to multiply everything by their top number. And what's 2's number? Well, 2's going to turn into 0 because 2 doesn't have a number. All right. So what we're trying to do is we're trying to find out when this point is equal to 0. So now or when the y is equal to 0, or when x is equal to 0, what should y be? Now we're usually used to our functions being y at the end and x at the other side, but thankfully it still works out no matter what variable you're working with. We're just seeing this as going downwards instead of sideways. That's like the only difference here. So now we're using the quadratic formula again, and we're getting 2 numbers. We get 8.5 and 2.816. Now, if we look back here, what number is going to be more realistic? The one that's up here or the one that's conveniently right here? I think we all know the answer to that. Or I guess it'd be like right here, like somewhere over there. That's different. Okay, so now that we have a number, we want to move 1 unit back. So we're subtracting 1 from that number. And then we can plug this in again. So we're plugging all these numbers back into the equation to see when this equation is true at a certain point. Then we get this answer, our 0.206. That would be the tangent of the line. I think I'm using the right terminology. That's the slope that line is going on. Great. Now, France is up 0-1, and this is looking very scary for Japan. Japan is already coming in as an underdog, and to have a goal taken from them this early on in the match, it's a bad sign. We'll say that much. So, the game starts back up, and Rin and Nasagi have the ball. Rin, possibly Japan's best member, we'll get into that later, matches up against Loki, and successfully nutmegs him. As we can see there, look at that. But Loki is the fastest under 20 player in the entire world, isn't letting that slide. Oh, spoilers. Rin gets a head start, but Loki's quick to catch up. If Rin is running at 8 meters per second and has a 10 meter head start, and Loki starts running at 4 meters per second and accelerates at 3 meters per second squared, will Loki catch up to Rin before he reaches his shooting range, which is 45 meters away? If so, where does Loki catch Rin? Alright, let's look at our equations. So for this, we're going to be using SVA principles, which is position, I don't know why it's an S, velocity, and acceleration. These look like physics principles. However, we're going to be using calculus skills in order to solve this problem. So, as we can see here, we have Rin speed as 8t plus 10, t being time in this instance. We have his velocity being his 8, which is the derivative of his speed, or his, oh my god, I keep calling it speed, his position. We can see this as, with respect to time, meters per second is the derivative of meters, if you catch my drift. And then his acceleration will be zero. He's not accelerating at any speed. He's going to be running at 8 meters per second the entire time. Now, we can see Loki's over here. He is starting at 0, right? But he has 4t, and he has t squared. Look how cool that is. But he has, it's hard to see, but I believe that is 3 over 2t squared. That's his position. His velocity is 3t plus 4, and his acceleration is 3t. Let's continue now. So, we are going to be, where did we continue? This is Ethan's work. We're going to be making each side equal to each other. because we're trying to find out which point they're equal to each other at. So now that we have them equal to each other, we're going to move everything over to one side. So we can use the quadratic formula to speed up this process. So now go all the way back over here. So we have two answers to this. Either they catch up at a negative point or a positive point. What do you think is more likely to be? Do you think they're going to catch up in the past or the future? I'm going to say probably the past. Or probably the future. Oh, it's not the past. So, well, they caught up at the past at some point, but then by them, whatever. So, we have 4.24 as our time, right? We're going to plug 4.24 back into our 8 seconds number and then add 10. This is our position number that we got from Rin. So, at 43.92 meters, Loki will catch back up with Rin and stop him from taking a shot, stopping another goal from Japan. Let's continue with the story. As we can see here, Loki catches up with Rin. Rin still tries to shoot, but Hugo manages to block it. It goes out of bounds though, and I believe it's Botcher there actually, goes for a corner kick. The corner kick goes to Isagi, and Isagi takes the shot. Woo! But Isagi's shot needs to be a certain speed if he wants to ever make it into the net. Let's see this. Isagi kicks the ball at t equals, you got this thing, which it looks, if we look over here, it looks a lot nicer than that. I just took it out of Desmos, I believe. How fast is the ball going at? 1 second, 3 seconds. If Isagi needs the ball to reach 30 meters per second, at what point does the ball reach the speed? Or at what point does the ball cap out? This is a limit question. We know this because we have x's in the top and bottom, and the x's are equal to each other, or the powers the x's are to are equal to each other, if that makes sense. We'll see in a second. So, we have our question, right? If x is equal to 1, this is a really easy question. The speed the ball is going to be going at is 170 over 7, which, hold up, give me 1 second, divided by 7 equals 24 meters per second at the 1 second mark. And that's pretty fast, right? If we assume the ball's going to constantly accelerate, after like however many seconds we need, the ball should be going super, super fast, right? Let's check out 3 seconds, right? We're going to have, plug in our 3s, we're going to have this, that's going to be 678 divided by 27. Now it's going at 25. Okay, so it's going faster, right? But it's not really going much faster, is it? Let's continue, right? So, we're trying to see when it's equal to 30. So we're going to multiply everything over. We're going to divide by, once again, I believe, what did I divide by here? Oh no, I moved everything over. And I got really lucky here because my numbers, which I picked out of the hat randomly, simplified really well, other than like the 30 term. We're going to do it the quadratic formula again, and we get two negative numbers. Huh, that's kind of strange, right? So Isagi's ball is going fast enough when it's before he kicked it? I think we can assume that doesn't make sense, right? Therefore, Isagi's ball is not going to reach the speed it needs to. How is that possible? Don't most graphs hit every point? Well, the issue is there is a horizontal asymptote in this graph, which means there is a certain number that when the graph approaches it, it won't reach, especially, or at least from one side. In this graph, as we can see here, right here, I tried to click my screen, but I can't. The graph is going to hit these points at a certain point. However, there is a horizontal asymptote on the right side of the graph that's stopping it from hitting these points. But where's your horizontal asymptote? We can plug a big number into our equation to find out, a big positive number, because we're looking at the positive side. The negative side we don't really care about. So, what's the biggest number you could think of? For me, it's probably going to be like 40-ish, right? But I mean, if you're smarter, you're probably going to know a bigger number. We can pick any number you want. But eventually, see the squared things we have? They're going to make our big number even bigger. Which means these numbers don't really matter at the end of the day. We're only really looking at the 56 and 2. What's 56 divided by 2? 28. So our ball's going to cap out at 28 meters per second. And Isagi will not be able to score another goal. Jeez. Japan's not doing very well right now. Let's hope that changes real soon. Alright. As we can see, Isagi's goal is stopped. This is actually just bad. I believe the goalie throws the ball to Loki, and Loki's on a run for it. But Shiguri is trying to keep up. Alright, look at this. So, this is probably my favorite question out of this entire thing. I tried to do it with like 2 speeds, but the other thing I was working with kind of sucked, and I just didn't want to do it like that. So this was my mini-max question, right? Chicory runs at the speed of 8 meters per second, but while running in a straight line, which I'm not too intuitive with this, straight line is running this way. Straight line's not like this. Straight line's like that. Okay. So while running directly straight, he accelerates at 4 meters per second. Loki makes it to the ball in 5 meters per second. What route should Chicory take in order to get to the ball fastest? And will Chicory even reach the ball? Let's find out. If we go over here, let's try and find an equation to this first. So as we can see here, we're trying to solve with respect to t, right? Actually, all right, we are back, everyone. So let's look at this equation again. We're going to be doing t1 plus t2. So that's going to be the total, or t, which is time 1 plus time 2, should equal the total. And we're doing this in regards to position. So if we look at the first question here, we have, let me turn that down again. We have b of t, or we have the, what's it called? The one physics equation. We're going to rearrange that so it's equal to 0. So we're going to be moving the position over. And then we're finding what t is equal to. So t is equal to this right here. And then on the other side, our position is going to be, so this is when we're running a straight line. This one we're accelerating, because we have acceleration in the equation. This one we're running on an angle. So our angle formula is going to be 100, which is the max distance we can run, minus whatever our p is squared, so the angle, and then plus 30 squared, because that's what we have to write on as well. And then the square root of that. And then we're going to be dividing that by how fast we're running at the time, which is taken by whatever our speed is at the time. So if I've been running for like a good 5 seconds, my acceleration would have increased, and therefore my equation down here would also have increased. That's where the 8p comes in. So now we have an equation. We got this thing right here. Let's go to the next slide and start solving. So we have this equation. We're going to have to derive both sides so we can find out when it's 0, and therefore when the best possible time to switch his path is. So as you can see, go down here. We're going to be, we can take away this negative 8 because it's just a number, and numbers get turned into 0. And then over here, once we derive this, it's going to be 1 over 2, so the 2 is going to be in the bottom. And then negative 1 over 2, so it's going to be the square root again, but on the bottom this time. And then we have to take the derivative of this too, right? So that's going to be, what do you have 4 on the bottom? We're going to bring another 8 up, basically. We have 8 on the top, 8 on the bottom, so it's going to be 1, and then root 64. And then we got this one. We have to use the quotient rule, which, spoiler alert, sucks. So take the derivative of this, derivative of that, all over this. And then we get this really wacky thing at the end, because you're dividing by the 64 over 8p. You're doing that. You can combine these together, but then you have to divide them, and then you get some, like, right here, you get, you're multiplying by the root 64 over 8p, but then you have 3 over 2 root 64, or not root 64 anymore, it's 3 over 2, 64 plus 8p. It's weird. I get it. I'm just not going to explain every single second of it. So let's continue. Oh yeah, how did I find the p value for this? I put a ton of effort in, and I put it into Desmos because I'm a little too lazy to find the p value of that huge equation. I don't know if it's possible to find it, because I'm pretty sure you're going to end up getting a Quartic at some point, I think. That's going to be weird. Some of the stuff's going to be weird as well. I just don't think it's worth it. Okay, here's our p-value, right? So now we're going to plug our p-value in the question again. We plug it in right here, and we're going to get a final time of 5 minutes, or 5.943 seconds, which is slower than Loki's time. Also, real quick, Loki's time changes multiple times throughout this entire thing. Don't ask why. We had 2 people working on the questions, and one of them, Jack Honka, kept changing his speed to fit the questions. So, yeah. I'm sure it would have been a lot cooler if his speed was constant the entire time, but like at the same time, it would have been really hard to do because I feel like all the questions need different numbers to work. Anyways, we can look here using the quadratic formula. This is the distance he had remaining. This is the 30 meters, not quadratic formula, Pythagorean theorem. And then this is the x distance he ran. So he ran this, then he ran this. He ran this part while accelerating. I hope you can see this mouse. I don't know if you can, because I paused for a sec, and I didn't know if I could see the mouse or not. Anyways, let's check my endpoints, right? So they aren't trivial in these questions. I did not write ERT. If he just runs straight diagonally, nothing forward, he's gonna have a time of that, and then if he runs all the way and the runs down, he's gonna have a time of that. So we found the best answer at the 5.9. Anyways, so Loki gets the ball, but thankfully we have the GOAT of this match, Karasu, stopping Loki from his run, getting the ball out of there, and inevitably passing to Hiyori. Where's the ball? Oh, look at that. That's cool, right? I like that. Okay, I'll shut up. Anyways, so Hiyori gets the ball. Hiyori takes the shot, and goal! It's the first goal for the Japan team. Japan tied the score up thanks to Karasu and Hiyori's contributions. All right. Now for another really, 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 really ugly equation. I'm not sure if you can tell, but I think it's really ugly. We got this thing right here. Once again, come grade 13, I'm going to stop doing these things. I'm just going to make my own equations. So we have Hiyori's shot represented by this equation. Let's provide a full graph analysis for the shot, including intercepts, asymptotes, and a sign chart, and anything else that I want. I did end behavior too. So let's go over here, right? We have this original equation. I'm going to save us a ton of time and say this point is 8 because I'm not using the cubic formula because that would be very, very hard. And I'm doing hard stuff on this question anyways. The cubic formula is a little too spicy for my liking. So now we plug everything into there. We get our quadratic formula, and we get 2 numbers. These are going to be when it reaches its max and min. Its max is going to be here. Its min's going to be here. And then the x-intercept's here. And then, if we take another derivative, we have another x that we have to work with. Ignore this really weird-looking chart. I just added some stuff around it just to illustrate my point. I could just have done the plus, minus stuff. Anyways, so what does this mean? It's going to be at right about here. So this is when it goes from trending upward, or from being concave up to concave down. We can see visualized here. We know there's no asymptotes because at no point can this graph be not able to be listed. Every number on this graph can be listed at some point. And then we can see here, as x approaches infinity from the x direction, y approaches negative. Wait, I think I wrote this wrong actually. Good thing I'm voicing this over, right, guys? As x approaches infinity, y approaches negative infinity. As x approaches negative infinity, y approaches positive infinity, as illustrated in this graph here. So now if we look at the my other little chart thing, we can see what's happening. A few of the important points are right here at this mark, which don't read this. I've erased it so many times because I kept doing stuff wrong. I think for a while I had a negative sign here and I had messed it up, and then I think I got a negative sign here as well. As you can, there's supposed to be a negative sign. I had a negative sign. I didn't have a negative sign there, something like that. It was stupid. I had erased it a couple times. You can see this much crashed out. But something like right here, right? It's going from negative to positive. That means it's going from concave down to concave up at some point. So, concave down like a frown, concave up like a cup. We can see here as well. It's going from I think negatives to positives. So at this point, it's all in the positive, or it's positive to negative, sorry. It's all the positives. And then it's going down to the negative, and then it's continuing down. It's here to over here. Get scrapped out a little. This chart, you have our y prime. Oh, prime is the one I was looking at. Okay, you got your y's, right? So you pick a point. Let's say negative 10, right? We plug it in and see if we get a positive or negative number, and that determines what our end behavior is. So if it's in the first one, if it's a positive number, it's going to be above the y or x-axis. If it's a negative number, it's going to be below the x-axis. In our second row, if it's positive, it's going to be increasing. If it's negative, it's going to be decreasing. And then in the third row, concave down like a frown, it's going to look like up like a cup. It's going to look like or up like a smile. I feel like up like a cup. Up like a cup kind of doesn't make sense if I'm thinking about it, but whatever. We'll stop debating that. All right. So Hiyori scores the first goal of the match, but Hugo is not letting this slide. As he talks to Sagi and kind of rage baits him a little, he starts off another play with him and Charles, passing it back and forth to each other. Look at that. I love these little effects. It took a little while to learn them. But Hugo goes for a shot, and let's see if he makes it. Boom! Right into the net. All right, let's continue. If the ball starts at this point and ends at this point, what are the vector, symmetric, and parasymmetric equations? Wow. Oh, Jack, that's such a good question. But where is the scalar equation? Well, it's really hard to do scalars in 3D. You can do like a plane for them, but to get a line, you have to be like Josh or something like that. Because Josh actually showed me today how to do it. It's just not something I was capable of doing for this question. So let's see the points of the line. We got 1, 15, 0.5, 2, 3, 0, and 2. In vector form, we're going to have x, y, and z here, and that's going to be equal to our starting coordinates. But what are these, you might ask? Well, this is our changing. This is our vector, I believe it's called. I'm really bad at the names, but this is our vector, right? So as t increases, let's say t is 1, we're going to be able to add these two together to get our x, y, and z coordinates. So if it's 1, you can add 2, you can add 15, which is 0, and you can add 1.5, which is 2. Oh my god, we got this point. So the way we find this is by subtracting this number from this number and then plugging it in. This number from this number plugging in, this number from this number plugging in, and then adding a t. Now let's go from vector to symmetric. Now, this is a pretty easy jump to do if we already have a vector form. All we really have to do is times these by t, and then rearrange so we have x isolated. So the first one's going to be x equals 1 over here, plus 2t, and then so on and so forth, right? So parasymmetric form is a little harder, but if you're a good mathematician, this should not be hard for you. What we're going to do is we're going to move this term over to the other side, and we're going to divide it by this term. So we have t isolated. So for example, let's look at our, let's look at z for example. So we're going to have z minus 0.5 divided by 1.5, which equals t. And then we have our answer. Easy as that. Now, because Japan's down 2-1, we're going to have to make a substitution, right? We're going to substitute the coolest guy of all time, Shido, on, along with Baro and Kunigami. So, what's happening? Karasu keeps taking a play upwards all the way to Shido until Baro interrupts that play. Baro dribbles all the way down. Shido gets the ball again. Wait, no, I don't know. I remember I structured this one like really weird, right? Anyways, so Shido gets the ball set down, but Loki gets on to Shido, right? Thankfully, we have the great Baro. Oh, that was really cool, actually. We have the great Baro to intercept the ball and continue this play. Look at that. Look how cool that is. I remember reading this when it came out. It's like really cool. Baro is going for a long range shot. The goal line is on the x equals 30 plane, and Baro is located at this coordinate. The ball travels on a straight line, with the vector being r equals this right here. Determine the coordinates where the ball passes through the goal line. Okay, let's see what we have here. We got our p and we got our v. We're going to be combining these into one question, right? So this is Ethan's stuff, so I'm going to be copying what he wrote down, and I don't really know what he wrote down. So let's see it here. We have this in our symmetric form. We're going to be rearranging it so we find what y is, because we're trying to find out the coordinates in which the ball passes through the goal. So we rearrange to find out what x is equal to. X is equal to 30. Sorry, I'm looking at what Ethan's writing. So we have t is equal to 2. We find that by isolating for t, and then we're able to rearrange to find our y and z coordinates, and we already had our x up here, right? So by finding these numbers, we're able to rearrange, get our x, y, z, and then the ball reaches the goal at the coordinates of 30, 4, and 2. There we go. Oh, sorry. I forgot this. We knew it's going to be 30, right? Because we mentioned up here, x is equal to 30. Okay, that's where that's coming from. And then now that we know x is equal to 30, we're able to put x into this equation right here, and substitute for t. And then, since we have t, we're able to solve for y and z because we already know what our t is. We just plug it back into that equation. Okay, that makes sense. We're working together on this question. That's so fun, Mr. Loma. I'm glad we're spending so much time together. Let's continue. Baro scores another goal, tying things up. But Hugo is not happy for this. He starts running up the field and sends a wild pass all the way to Loki. Let's see. This is okay. Little story time, and then I'm going to pause again. So, Gilowitz showed us a really cool method, or he didn't show us. He had a question about it, and then in his answers, he had a really cool method of solving this question. However, I couldn't find the really cool method to solve this equation, so I searched everywhere online to find a way to solve projectile motion questions where you have a degree simple, or like where you don't have the degree simple. I ended up finding a question online, and I did some like looking into the question because it's like one step later on where it has a trigger identity that I didn't know. Then I looked up like a trigger identity through online, and I figured it out. But yeah, first let's derive the big five equation. So we see here. Actually, that's where I'm going to stop for a sec. All right, the video's nearly done. I'm going to skim past this part. I wanted to put a code in the video to be like, oh yeah, if Mr. Loma made it this far, say this. So Mr. Loma, if you made it this far, put a 23 in like whatever feedback you give this. Okay, that's my goal to you. Okay, so deriving the big five equations, we got this, and this, right? So the derivative of this is this, derivative of this is this, derivative of this is this, right? So our first one is going to be this right here. No way, that's so crazy. Our second one is going to be the opposite of this. So this would be if it's going in the opposite direction. Our third one, we're going to be combining the two, could be equal, making them equal to each other because they're both equal to d. Rearrange, that's our third equation. Our fourth one, we're going to plug one of these guys into this. We got our fourth one. Our fifth one, we're going to plug something in here. I think it's, what did I use? I used, I thought I used this. I don't know. I used something, put it with something else. Ta-da, another equation. Awesome, right? Super fun. I added a little ta-da there as well. So cute. Great. Now we have our x direction and our y direction. So this is what we have to do for projectile motion questions. Now that we have the big five derived using physics principles, we're able to use big five principles to derive the rest. So our velocity, as mentioned before, is 22 cos theta. Why are we using cos? Well, when cos is 0, which would be if it's straight on the ground, that means is cos, hold up. Let me check my work. Cos 0 is equal to 1, yeah. So if I'm kicking the ball straight ahead, and it's only on the x-axis, our speed's 22. But if I'm kicking it straight up, I'm posing, I'm also kicking it, but like you can't see it. If I'm kicking the ball straight up, then it's going to be 22 as well. So if we're on an angle, they're going to be opposites of each other, kinda. Move it around, all that stuff. Anyways, let me continue so I don't waste too much time. Our acceleration, no acceleration going up sideways. Acceleration due to gravity is 9.8. We have our distance is 35 and our height is 2. I think I mentioned that in the previous part. So now we're going to be using our big five equation right here. Now it doesn't look like a big five equation, but it is. We have velocity, and then maybe it isn't a big five equation because I forgot my time. Okay, I forgot time. There should be a time there. We're going to be dividing by that, which gives us d over v cos equals time. Time is going to be the thing that we can compare the two because everything else is different. I know it says d in both of them, but one is a dx and one is a dy. We're going to rearrange to get to this, and then we're going to further rearrange till we get to this. And then we're going to plug our numbers back in because it's easier to do without the numbers. Gilbert does it like a really cool way. I forget what he does though. This comes down there, and then I think you have a theta or something theta left over. I think it's like maybe I don't know. It was really cool. I was going to ask him about it, but it's like, I'm doing this the day before it's due. I'm doing the voiceover the day before it's due. So I didn't have time to ask him like, hey, what was like the really cool thing that you did? Anyways, so let me continue here. You got this, you got this, you got this. The thing I was confused on is cos to tan, or 1 over cos to tan. There's a trigger identity for it. I was going to pull up like a little chart of it. I didn't. I forgot about it. It's not on my slideshow, but it's a trigger identity. It works. It follows math principles. So then we go here, we go here, we go here. And then, because we have a tan squared, a tan, and a regular term, we're going to do Pythagorean theorem, but instead of using x, we're going to use tan. It's really cool, I thought. Once again, I'm learning all this from a video, so I hope it's legit. Maybe the video is lying to me. But we're going to have this and this, and that gives us two different numbers, 66.70 and 26.57. If you're taking a shot and you want to catch a player, and they're going to reach the player at the same speed, I think we're going to want to take the shot that's higher up, just a hypothesis. Anyways, Loki scores another goal. But Asagi's like ready. He's locked in now. He matches up against Hugo, goes the other way, but suddenly Rin being a bum, tries to also shoot the ball at the same time. And get ready for this. That's a highlight of my presentation. Everything's downhill from here. Got this little thing in the ear. Ball hits the crossbar and goes away and gets to Julian Loki. Or Julian's his first name. Anyway, gets to Loki. After this devastating miss, thanks, Rin, Loki speeds past everyone while Sagi remains still. Sagi's standing 30 meters from the sideline while Loki runs at 6 meters per second. Once again, his speed changes. To determine the rate of distance between Loki, which is 40 meters away, or when Loki's 40 meters away from the starting point. Okay. It says Batra here. That's because my good friend Ethan thought we were doing Batra instead of Loki, because I didn't really tell him the instructions. Distances between these two. So let's find what terms we know. We know our d of x with respect to d of t is 6 meters per second. That's going to be the speed it's running at. And, oh my god, I can't see this. D of d is equal to 40. Anyways, so we have this equation right here. We know it's going to be a triangle because it's, or we know it's going to be a Pythagorean theorem because it's a triangle. I had it the other way around. We're going to take the derivative of each side, which gives us this. We have to rearrange it a little. We're going to plug in our numbers, our 40 from here, our 6 from here, and our 60 from some... where did he get 60 from? Yeah, where did he get 60 from, huh? Is there a 2 I'm missing? I don't know. He got a 60. Let's just continue. I don't know if you made it this far. We'll see. You got a 60 somewhere. You do this, you get your 4.8 meters per second. That's going to be the rate that it is changing at. Oh, wait, is it here? D60. Oh, there we go. Look at that. We found it. Okay. So here's the Pythagorean theorem to find out what a D would be. 30, 40, square each side, square root the total. There we go. And then the distance between them at 40 meters per second is 4.8 meters per second. There we go. Loki scores another goal, but Asagi is still riled up. They still have one more loss left. They're in the qualifying stage. They've won one, lost one. They're going up against England next, and they need to win this match, or else they're not playing in the World Cup. Oh no, or they're playing in the World Cup. They're not playing in the tournament-style World Cup. Anyways, match is over. Japan clearly can't use calculus to the best of their abilities. Boo! Boo Japan. Learn calculus. France is clearly better. Okay. Bonus question. This is when you could click off. The video's done. Everything else is just me messing around because I'm bored. Okay. So Ethan sent me this, but he didn't I didn't crop this out. I don't think I cropped this out. This is just already cropped, right? I'm gonna try and figure out what this guy is. His question is. So 4.02 or negative number. It's probably from this, right? So I think this speed something's traveling at. He's using big five equations, which he derived. So 7 is going to be his velocity. I think that's just gravity. That's my hypothesis right now. He's using gravity. And then 53 is probably the height. So I think he's throwing something up, it looks like. So my guess is So yeah, he's standing at 0. Something goes up 53 meter, maybe? 50? Is that a 53 or 50? Huh. Where did the 2 come from? I don't know. This is confusing me. My guess is he's throwing something up and then it's falling back down. And it's falling probably before the ground, because I know Gillett did a lot of those questions. As it's about to hit the ground, it's falling at that speed. That's my guess. Anyways, bonus question. Rin. This guy is a bum. If Rin has after the X is equal to X, 5 fans, how many fans does he have after 1 day, 1 week, 1 month, 1 year? As we can astutely see, it's being divided by 0. So it's 0 fans. I hate this guy. Anyways, thank you so much for watching. Hope you have a rest of your week. I'll see you later. Au revoir, as